effectiveness of explainable artificial intelligence in calibrating trust in domain experts. Finding out how effective this actually is what I've been working on during my time at Shinto Labs. Shinto Labs is a small company that specializes in developing data-driven solutions for municipalities. Fortunately, they have allowed me to work and collaborate with them on their automatic document classification AI. Now, this AI assists municipalities in assigning case types to documents, because some municipalities receive over 10,000 documents per month. Previously, a municipality employee had to inspect these documents manually and then assign a case type. Currently, with the AI developed by Shinto Labs, the AI first inspects a document and provides a suspected case type. Now, the municipality employee simply has to verify this case type or correct the AI. This is a prime example of an AI-assisted decision-making problem. When the AI provides recommendations to a human, we can consider the AI and a human to work in a team, such a human-AI team. And human-AI team performance is primarily a product of trust, because the employee has to accept correct recommendations, so trust the AI when it is correct, and reject and correct incorrect recommendations, so distrust incorrect recommendations. The problem with trust, however, is that it is rather difficult to calibrate. When humans overtly trust an AI, then they don't think critically anymore, and they accept too many incorrect recommendations. When they overly distrust the AI, on the other hand, they don't bother looking at AI recommendations at all and then generally ignore everything. Our goal is to be somewhere in the middle. Our goal is to have the human's trust in the AI match the AI's trustworthiness. And it turns out that human-AI trust works rather similarly to trust between humans. The primary difference, however, are that trust in AI, the AI performance is key. When we trust our colleague to do something, for example, and they mess up, then we trust them a little less, and we're less likely to ask them to do something for us in the future. Similarly, this works the same with AI. If we trust the AI to do something for us and they mess up, then our trust diminishes and we want to rely on it less in the future. Although this diminished trust is way bigger when regarding AI other than humans. So how trust usually develops within human-AI teams is that humans initially have an assumption of high performance. When we hear about an automated system, we expect it to do really well. However, once we see the AI make a mistake, such a mistake violates our assumption of high performance and our trust drops substantially. We want to break this pattern. Fortunately, literature provides a solution. Explanations. Providing insight into how an AI processes information differently from us and the internal reasoning used by the AI fosters understanding and compassion, and that allows our trust to not drop as severely as it otherwise would. However, the automatic document classification AI is an opaque model, and to provide explanations for opaque models is rather difficult. This brings us to the realm of explainable artificial intelligence. Explainable artificial intelligence, or XAI, are techniques to provide explanations for opaque models. What it means for a model to be opaque is that we could theoretically do all the computations the AI does by hand. Doing so won't make you very happy, but more importantly, it won't provide any insight either. We want to learn how the AI reasons from doing the computations. That is what makes a model opaque and what makes it so difficult to provide explanations for such a model. But it is possible. It has already been done in various AI-assisted decision-making problems. XAI has been implemented successfully. The primary problem with these scenarios is that they either are low stakes and don't really have any real-world applications, such as chess, for example. It happens in the real world. I understand that, but there's nothing really at stake. Or there are real-world applications, such as house price prediction or even student admission, but these experiments have been done with non-domain experts, so layman people that don't know anything about house prices are no experts in that domain, and they do house price prediction. We want to verify if the effects of explainable AI found in these scenarios apply to real-world applications with domain experts as well. We do so by answering the following research questions. Does XAI increase reliance on AI recommendations? Does team performance increase with XAI? And does XAI mitigate the drop in trust when AI is observed making a mistake? That takes us to what I've been doing in my time at Shinto Labs, implementing explainability in the existing AI. We chose to use CHAP, which is a feature importance explainability method, and it's based on Shapley values, a concept that originates in game theory, used to compute a player's contribution to a goal while working within a team. For us, this means that we compute every word's contribution to the end result, the recommendation of the AI. And it looks somewhat like this. In our example, the AI is 95% certain that the document pertains municipal toddler care. And the most important words in determining or coming to this conclusion and recommendation are toddler daycare, hooray, daycare, toddler vacancy, well-being, villa, and toddler daycare again. The intuition is that when a municipality employee observes this, all this information, sees that the AI is rather certain, and based on these words, they can decide to trust the AI because everything makes sense. In order to generate explanations for the AI recommendations, there are a few challenges that need to be tackled. The primary challenge is that the words provided to the AI are also used in generating explanations. In order to generate suitable explanations, the current AI's natural language processing pipeline had to be adapted to suit our new needs. And this is all the realm of natural language processing, a subfield of linguistics, computer science, and AI that focus on translating human-readable natural language data to a format that computers can understand. As you can imagine, a computer cannot read the way you and I do. A computer or an AI has no use for grammar that link words together, because the AI in this project uses term frequency inverse document frequency, which is an extension of word count, where it counts how often a word occurs and it compares that to how many documents there are that also contain these words. If we're counting words, then grammar has no use. But there is also another challenging part, that words of different forms basically mean the same thing, such as giving and given. They are basically the same word give, and to make this work as input for our AI, we have two options basically. The first of which was already implemented in the old natural language processing pipeline, which is stemming, and it's basically cutting parts off a word to reduce it to its stem. The alternative is lemmatization, which reduces words to their base dictionary version of a word. An additional advantage of lemmatization over stemming is that it's slightly more powerful in terms of grammar, as given and giving are both reduced to give in the lemmatization example. But also we have the word apple instead of apple, which is eventually used for explanations as well and provides more coherent explanations. It is already mentioned that in human AI trust, performance of the AI is key. So to improve trust, we also wanted to improve performance. This is something I also spent quite a lot of time on. And the improved AI is based on the existing model's architecture, which is the architecture of a multi-layer perceptron. And the goal was to create the simplest model that performs best. As we bound the network in depth to 2 layers deep, we were able to optimize the model complexity using the layer width. We also changed from word count to term frequency, inverse document frequency, and eventually did manage to improve the AI quite a bit. Reduce the amount of trainable parameters from 21 million to 2 million, reduce the words in vocabulary, primarily due to lemmatization over stemming, and even increase the classification accuracy. Now that we have the AI with explanations, we also want to test if explanations do foster more trust. To do so, we designed an experiment. We chose to include 3 case types in the experiment to make sure that the experiment isn't too complex, as more case types would needlessly clutter the experiment with complexity, but also ensure that trust generalizes to the entire AI and not just to the AI's ability to classify a particular case type. We divided participants into a test group that was provided explanations and the control group that were not provided explanations. Participants were told that they are responsible for the correct labeling of documents, and for every trial they were asked if they wish to rely on the AI or not. The experiment also consists of 2 phases. In the first phase is designed to answer research question 1 and 2. Does trust increase and does team performance increase? It consists of 12 trials where 50% of the trials the AI suggests the correct case type. The 3 case types are divided in groups of 4, like this, where they have a pair where the AI is very certain and where the AI is less certain, both of which one of them is correct. And we wish to answer the hypothesis, do participants in the test, or we wish to verify these hypotheses, participants in the test group trust the AI more often, and participants in the test group score higher. Phase 2 is designed to answer the 3rd research question. Do explanations mitigate the drop in trust? Phase 2 differs from Phase 1 in that feedback is provided. In Phase 1, the participants are not shown if the AI was correct or not, so they could not see if the AI made a mistake. The 5 trials in Phase 2 are divided as follows. First, 2 correct trials are provided to provide a base level of trust, is the intuition. Then the AI makes a mistake and provides an incorrect recommendation. Finally, 2 more correct trials are provided. The hypothesis is that trials 4 and 5 are trusted less than trials 1 and 2, but this difference in trust is smaller in the test group because the explanations would mitigate this drop in trust. In order to recruit participants, we used the contacts of Shinto Labs and extended this with personal contacts as well. And there were a few requirements. Participants had to be a municipality employee, understanding the implications of the work that has to be done, and understanding the case types is very important. They have to understand the case types used, because otherwise the explanations would not make sense, and then the entire experiment doesn't test what we want it to test. And we would like them to have experience working with the AI already, as previous literature has shown that people tend to have too high expectations of unknown AI. So, did we verify the first hypothesis? Participants trust AI with explanations more. Unfortunately, we didn't. Instead, the exact opposite result was found, which directly contradicts with our hypothesis. And this is most probably a result of an unfortunate distribution of participants. There were not a lot of participants, 8 in total, and these came from 2 municipalities, or 3 municipalities rather, 2 of which had experience working with the AI, and 1 which didn't. But there was 1 municipality that had worked with the AI for a very long time. The other one only worked with it for a month. And we can see that the participants from the initial municipality trust the AI way less than all other participants. Unfortunately, the distribution of participants was a little skewed due to a low response rate, which is why most of the test group consists of participants from the initial municipality. So while we cannot really draw any conclusions about our first hypothesis, we do find that trust in AI decreases over time after working with it. Our second hypothesis is slightly more promising though. Participants with explanations score better. It turns out that they do, to some degree. The test group was provided explanations, and they correctly trust and distrust the AI 25% of the time, as compared to the 45% in the control group. This difference, however, is not large enough to be statistically significant, but it does hint that XAI might be effective in calibrating human AI trust. Basically, more data is required to draw any conclusions on this matter. Finally, our third hypothesis, drop in trust is mitigated by explanations. Unfortunately, the experiment was not able to capture the drop in trust entirely. Most likely, the length of phase 2 of the experiment was too short for trust to actually develop over time, and observing only 1 mistake was not enough for trust to drop. Because we didn't want to ask too much of the time investment on behalf of the employees. We tried to keep this phase, or the entire experiment, as short as possible. Unfortunately, slightly too short. However, in conclusion, municipality employees have reported a decrease in trust. Their experience is in line with existing literature which suggests explanations. I have adapted the existing AI developed by Shinto Labs and extended it with explainability. And results show that trust does decrease over time, and XAI is hinted at being effective in calibrating human AI, in increasing human AI team performance. There were some limitations. There was a low response rate from municipality employees, which is understandable. They have a job, they have much to do. But also the case types used for this particular experiment were slightly ambiguous. The municipality employees have reported that they themselves also find it difficult to distinguish some of the case types used in the experiment. Having been shown examples of other more clearly defined case types, they noted that explanations there does really help them trust the AI. So that would be something I would definitely do different in the future. And the experiment was slightly too short to really capture the drop in trust. But I do hope that this research can serve as a stepping stone for future research to discover how to effectively implement XAI as explanations to calibrate trust in domain experts in real-world applications, such that we can all benefit from power and opportunities that AI provides.